In lab, you were looking at momentum and energy and collisions. Now, remember, there's various different kinds of energy. There's kinetic energy and potential energy and elastic energy. And we looked at actually elastic potential energy and kinetic energy in this lab. Quick review, remember momentum is mass times velocity. It's a vector quantity because it includes a magnitude, how big it is, as well as a direction. Now you should also keep in mind there's a few different definitions for momentum. One of my favorite ones is how hard it is to stop something. The more momentum something has, the harder it is to stop. And if you think about that, there's two ways you can give something a lot of momentum. You can make it really, really big, give it a lot of mass, or you can make it move really, really fast. Kinetic energy, of course, is a scalar quantity. It has no direction. That's because the velocity is squared. Even if it was negative, the square would take care of that. It would cancel out. So it doesn't make sense to talk about negative kinetic energy. Kinetic energy is a scalar quantity, 1/2 mv squared. Momentum, as you recall, is conserved. That means the total amount of momentum is constant in a closed, isolated system. Remember, closed means we're not going to gain or lose any mass, and isolated means there are no outside forces that are acting on our system. Okay? Energy is free to change form from one form to another. That means you can change elastic potential energy into gravitational potential energy into kinetic energy, but there's also thermal energy, which is the energy of atoms, and it's perfectly legitimate to change mechanical energy into thermal energy. So when you rub your hands together, you are changing chemical energy into mechanical energy to make your muscles make your body move, and then the friction is taking the mechanical energy and converting it into thermal energy, which warms up your hand. So there's a whole bunch of energy conversions that are there. So while the overall amount of energy is constant, the overall amount of any one type of energy is not. So we always have energy conversions going on. We put this together in collisions and we end up with a couple different kinds. Inelastic collisions are the sticky collisions. That's when you smash two things together and they stick. They don't bounce apart, they stick together. And when this happens, you do not keep a constant amount of kinetic energy. Best example is when you have one cart that smashes into another cart. This one's initially moving this way, this one's initially moving the opposite direction. Now, these two things both have kinetic energy. If this one has mass m and this one has mass m and this one is moving with the velocity v and this one is moving with velocity v, I guess this one would have to be negative, then we can see that the kinetic energy over here is equal to 1/2 mv squared and the kinetic energy over here is 1/2 m negative v squared. Well, that means I just have 1/2 mv squared plus 1/2 mv squared because the negative cancels, and I have just 2 times a half, so just 1 mass times velocity squared. So the total energy of the system is mv squared. That's before the collision. Now I want you to think about this in terms of momentum, because in terms of momentum before the collision we have mv plus negative mv, which gives me 0. So the total momentum before they collide is 0, which means the total momentum after they collide is also 0. But since these things stick together in the collision, after they collide, what we have is two carts at rest. Velocity is 0, which means the kinetic energy is now 0. All that kinetic energy that the carts had has been dissipated, changed into some other kind. It made a sound when they hit, so that's energy in a wave to make the sound, and some vibrations there. The thermal energy increased. The plastic ends are going to be a little bit warmer. Okay, so the kinetic energy is no longer kinetic energy, it's some other form of energy, but momentum was still conserved. You started with 0 momentum and you ended with 0 momentum. Doesn't matter what the collision is, as long as it's a closed, isolated system, momentum is conserved. An elastic collision is when you have things that bounce apart. So if you didn't have these carts stick together but instead they bounce apart, what you usually see is a little bit of loss of kinetic energy. But if your collision is perfectly elastic, then kinetic energy is conserved. So you had the magnetic ends of the carts, so they actually never quite touched. The magnets pushed on each other and the carts would push apart. We do see a little frictional slowing and we do see some change of kinetic energy, but in the perfect world, in a perfect inelastic collision, or a perfectly elastic collision, that says inelastic, it should say elastic, in a perfectly elastic collision, kinetic energy is conserved. Okay. Now you did look at one more type of collision or interaction called a superelastic or explosion, and this is an interesting one because it actually increases the amount of kinetic energy. Now you cannot create kinetic energy, but you can bring it in from some other form. So we did it by using a spring. We had potential energy stored in the spring. Now the reason this is still counting as a closed isolated system is because that spring was internal to the system. It was a part of one of the carts. Bombs or bullets or whatever, they do the same thing, follow the same rules, except instead of a spring, they use chemical energy stored in gunpowder or some sort of explosive. And in a superelastic collision, momentum is still conserved. And if you think about it, two carts at rest, and then you push the little release, and the two carts move in opposite directions. And since these momenta are going to be opposite, you add them back up, and they will add back up to 0. Okay? So no matter what the collision is, momentum is always conserved, but kinetic energy can change. And we have inelastic collisions where kinetic energy decreases, elastic collisions where kinetic energy remains constant, and superelastic collisions where kinetic energy increases.